But it's a pleasure to have Shreya Dave with us today. She is the CEO of Via Separations, a company that's looking at how to take advantage of energy efficiency opportunities across the manufacturing value chain. Shreya got her PhD at MIT with Professor Jeff Grossman, looking at some very novel separations techniques with graphene oxide membranes, and maybe it was thinking along those ideas that got her to spin out Via Separations with some of her colleagues. That's a very well recognized startup company already, and I look forward to Shreya's telling us some more about that work and that model and where you're headed with that. So thank you, Shreya.
All right. So I am, as Bob said, part of the MIT story, part of the MIT ecosystem, and our company, Via Separations, is just as much part of that story. The very original research that was before my time in Professor Grossman's lab was funded by a MITei seed grant that kind of led to a project that actually could get its own funding, which led to ultimately this company over the last, I guess, about 10 years now. So this is going to be a little bit less of a physics lesson than the last one, but and a little bit shorter of a timeline. But today we're going to talk a little bit more about as a whole, industrial decarbonization is going to require a lot of things. It's going to require fusion. It's going to require storage on the grid to be able to handle renewables. It's going to require improving processes to make cement or steel. And that's all pretty well understood. And I think the kind of the lost soul in industrial decarbonization is energy efficiency. And I say that because energy efficiency is everywhere. You know, we're familiar with home energy audits or ways to, you know, use your Nest to turn down the temperature. But at the industrial scale, you're actually looking at much larger quantities. If you can switch processes to improve the efficiency of different processes, but it's distributed. And I know many of you on this call are representatives of companies that make something, that manufacture something, and how do you go about improving the energy efficiency of a large power plant or a large manufacturing facility becomes quite overwhelming. Well, we narrow down into one specific thing, which is separations, manufacturing and separations. It is just double checking that you have the right screen here. You do. 12% of U.S. energy, which is the amount that we spend in gasoline in cars and trucks, you know, in the country every year. So it's this enormous amount. It doesn't get talked about a lot, and yet we could save about 90% of that energy. And so the analogy I like to use is a pot of pasta. Today, we do most separations like taking a pot of pasta and boiling off all the water to get to the pasta at the bottom of the pot, instead of pouring it through a strainer in your sink, which at the industrial scale is 50% lower capital costs, 80% lower total operating costs. And that leaves us with the opportunity to switch from the boiling, the thermal or the evaporation or distillation to a membrane-based process or a strainer-based process. We make that strainer, and we make that strainer at the nanoscale so that we can filter things that we couldn't filter previously. I know we got a little bit of an introduction, but I thought I'd give a little bit of our founding story because MIT and because the Energy Initiative and because ILP have all been so involved in how we got to here and where we are now. I spent 12 years at MIT before spinning out Via Separations. I did my undergraduate. I started in 2005, which I say not to date myself, but to say that was the same year that the Energy Initiative started. And so I kind of grew up with this focus on sustainability, focus on energy technologies, and developed this kind of deep, I would say lifelong passion for market-driven solutions. You know, how do we make the world more sustainable, more energy efficient in this case, but do it in a way that is market-driven? After defending my PhD, actually 4 years ago yesterday, I had absolutely no plans of starting a company. And about 4 years ago next week, I read a paper that completely changed my mind. It was a commentary in Nature that talked about this 12% of US energy consumption being dedicated to separations, and turned to my advisor and my colleagues, so Jeff Grossman and Brent Keller, my co-founders, and said, hey, should we see if this membrane that we worked on in grad school has these commercial applications in different chemical industries? And we spent that summer after we graduated, after Brent and I graduated, talking to different customers and doing a program called NSF through the National Science Foundation, CORPS, like I-Corps, like Peace Corps, but for innovation. And that really led us to be convinced that there was a market opportunity. So completely changed the life plans and launched this company Via Separations in 2017 with an initial investment, seed round investment led by the Engine. And so I know Brandon talked a little bit about this, but the Engine is this collection of technology companies solving real problems and frequently coming out of a lab and requiring that kind of bridge into deployment, into commercialization. You know, for CFS, it's going to be another 10-ish years. For us, it's going to be another year or so, and yet a year is a long time in the venture capital world. And so the Engine is specifically structured to be able to approach technologies like ours. Along the way, obviously support from a number of other places. We sit at Greentown Labs, which is an incubator, clean tech incubator based in Somerville. We've received funding from the Mass Clean Energy Center, from the NSF, the SBIR program, and obviously, I mean, I could name the number of mentors and advisors, some of whom I've seen as participants on this call that have got us to where we are. But I really did want to highlight the fact that there needs to be some pathway for this innovation to happen, for taking academics like us and turning us into market people or managers, for taking technologies and turning them from proof of concept into products. And those pathways are ones that are really, really important. The story of VIA is a story of scale. I mentioned scaling us as academics into managers, but also scaling up the technology. When we left the lab in 2016, you can see this little tiny dot on the slide here, refers to the size of the membrane that we could make. And we've scaled up about 18,000 times since then. We've developed a roll-to-roll manufacturing process. We can work on large areas. We don't need to work around defects or things like that, and we can make this at a cost competitive price point, right? So in addition to getting everything to work, we need to do it in a way that makes it economic for our industrial customers. Otherwise, there's no reason for them to adopt a new technology. So I'm gonna jump back into the VIA story and where we sit in context with other technologies. We're a filter company, we're a membranes company, but we don't filter water. We filter everything else. This chart shows along the x-axis different chemical environments that are used in industrial settings, whether it's pharmaceuticals, whether it's chemicals, whether it's food and beverage, which are shown on this chart. The y-axis is temperature, and you can see that we fondly call this plot the bubble plot. But you can see these bubbles, the yellow and the green and the blue, are centered around water. They're centered around lower temperatures, and they're actually centered in places where industry doesn't really benefit from them. Water filtration, on the other hand, completely benefits from them. So your traditional reverse osmosis membrane sits right around here and does great in terms of saving energy and capital costs for water desalination, but doesn't necessarily transfer to other industries. The technology that we've developed is based on graphene oxide, which is a cheap cousin of graphene made from graphite, which is just pencil lead. You chemically explode it, and then we put it back together. And our intellectual property is how we put it back together and how we manufacture it over large areas, specifically in this roll-to-roll process that we've developed. And so we're a chemistry company, kind of deep down at our heart. We're doing chemistry, and we're scaling up different chemistries. And I'll bring it back to the bubble plot for just a second to talk about the pulp and paper industry. And so I realize I've gone through this quite quickly, but I'll slow down a little bit and talk specifically about this application because it's so impactful, but also because it is our first market. It is where we are going to start selling, start doing commercial deployments, and be able to do that at scale for both economic value, but also an energy impact. So there's not much you need to know about the pulp and paper industry. There's two, maybe three things that there is to know. The first is, actually there's four things you need to know. The first is that it smells really bad. And if you've ever driven by a paper plant or a pulp mill, which is one and the same, all across the highway, you'll know because it smells like rotten eggs. That sulfur process is what is used to take the sugars that turn into paper and dissolve out all the other stuff. The second thing you need to know is that when you're driving down that highway, the biggest building on that facility, the tallest, the widest, it's the one that stands out on the landscape, is the recovery boiler. And the recovery boiler is there specifically to do a separation. And that separation accounts for about 3% of all US energy. Pulp and paper itself accounts for making paper like Amazon boxes or diapers or toilet paper, you know, when there's a pandemic or something, is about 7%. But that one separation process is about 3% of all US energy consumption. The second thing, or the third thing, I guess you need to know, is that it's very capital intensive. Those big recovery boilers, the evaporators, the thermal train that gets you to be able to make paper are large assets. They're huge repairs, huge maintenance costs, huge construction costs. And what we do is we augment those assets. We don't try to replace them, and we don't try to change them, but we augment them. And then the last thing that you need to know is that the paper industry is growing, and that was news to me. But when you do look at e-commerce, like I mentioned, Amazon cardboard boxes, which I've probably got two out front right now, or wound care, or diapers, or compostable cups. All of these are paper products, and the industry, although newspaper and glossy magazines are shrinking, the industry as a whole is growing. So what we're able to do is come in a very significant way to a concentration step, to a separation step, and reduce the energy by half. So take that 3% of US energy consumption and cut it in half. And that's where it starts to get interesting for us, because as a team, we are motivated by that needle ticking, that movement on energy consumption. And we can do this in pulp and paper, we can do this in petrochemical refining, and we can do this in chemical refining, and in semiconductors, and in, you name your sector, your manufacturing sector. And I can tell you exactly what is my favorite separation, maybe my favorite one because I think it's interesting, and maybe the one that I think we have the most energy impact on, efficiency and cost impact on as well. And so focusing in on being able to scale this technology across those industries is sort of the next phase of our company. So bringing it back to pulp and paper, this right here is a recovery boiler. They don't actually have windows, but this graphic shows them. So don't expect to be able to look inside a recovery boiler anytime soon. These evaporators, and this is the via separation system. It's a truck size system. It's a semi truck. It's a 60-foot shipping container that goes before the evaporators and pre-concentrates the system so that we can cut the energy consumption in that process. It is enabled by the membranes. So it's not that the pumps and the pipes or the shipping container is new, which is good because that's not our core competency. It's the membranes that are able to resist fouling. They're membranes that are able to handle the harsh conditions. So if you were to take a water filtration membrane and put it into this paper mill environment, it would last, we haven't tested it, it would last, I think, 10 minutes. The temperature and the pH would melt, swell, and dissolve the membrane all at the same time. And the technology that we've developed is robust enough to handle those harsh conditions. It's got an anti-fouling property so that it doesn't gunk up as quickly as a polymer membrane does. It will gunk up, and we do have to clean them, but that's all built into the economics of the process. And we're able to put them in modularly, which is actually a really cool and unique property of membranes in the sense that when we demonstrate one at full scale, all we have to do is put in 100 of those. All we have to do is make and put in 100 of those, as opposed to showing them at different scales, getting larger and larger, as a reactor or a storage or something like that may require. And the market opportunity is significant. So there's a number of things shown in this graphic, which I won't get into unless folks are interested. But at a high level, there's about a $50 million market opportunity per mill per year. And that's a part energy savings. About 10 million of that is energy savings, and about 40 million of that is actually allowing additional product to run through the whole system. So you pre-concentrate a flow, you're able to actually put more flow into that evaporator. And so the combination of those two actually means a lot, both to the mill as well as to us. And so we've developed I won't call it innovative because folks have done it before, but maybe a different way to think about the business model in a service model. And so we're going to borrow from what gas compression companies, or like Praxair or Airgas companies like that do, and sell our product as a service. And we do this for three reasons. The first is that it reduces the educational barrier. It allows us to enter pulp mills with no additional training, which is something that we've heard from the industry is desired. The second is that it takes the risk off of the pulp mill manager, in the sense that he is not paying unless we're producing. And so it's a service model. Unless we're successfully producing, they're not paying us. And third, it allows us to capture value, which we then plan to reinvest into development activities that allow us to go on to the next application, kind of in our sequence of different applications. And so this model means that there's a significant market opportunity. There are about 120 mills in the United States that are suitable, that kind of fit all the criteria for us, and more than 3 times that globally. So there is a very large dollar value, which tying it back to the beginning is important because of our mission of market-driven technologies, having this pull, having the desire to scale this, because energy efficiency doesn't happen unless there's an economic incentive, at least in my opinion. And so pushing that is really important. So in total, this is my last slide, but in total, we've got nearly a gigaton of CO2 in the pulp and paper industry alone. And as we look forward, we're looking at things like cleaning isopropanol for semiconductor applications, or separating olefin and paraffin gases in petroleum refining, or concentrating acids in chemical production for some of the chemicals that we use in products every single day. So we get excited by reducing the embodied energy in materials and products that we're using every day. Thinking to kind of the world right now in so many industries having slowed down, manufacturing goods has not entirely changed. Paper mills, we spoke to one potential customer. He said to us, we make 40% of the country's food packaging on this site. We cannot shut down. And so these are industries that are really fundamental, really critical to society, even when a lot of things have shut down. And it's pretty poignant to look around and see, with so much less transportation, the globe is using a lot less energy in transportation, but we're not using any less energy in toilet paper production. And there is only going to be one way to do that, which is through technology. So that's what I have here. I'm super happy to answer questions, but I'm also interested to hear if there's any applications that folks are excited about. We can talk about that offline, and to bring it back to MITei and to the ILP. I think it's pretty important. One of our biggest potential customers was an introduction through the ILP. We got our start sitting at MITei, and like I said, you spent many years in the ecosystem at MITei, and I guess I can't say I'm out of it if we're still part of the engine. So thank you very much.
So we have a number of questions already in, and I'll start with some of those. One is a fouling question. So back to the paper and pulp, as some polymers come out of solution, Do those cause fouling problems? Or maybe you want to speak more generally, if it's since it's membrane technology, how do you deal with fouling issues?
Yeah, obviously, this question came from someone familiar with membranes. Fouling is the number one challenge for membrane technologies in challenging environments. In a pulp mill, this black liquor stream, which I referred to as the single concentration stream, black liquor is a soup of all sorts of things. We don't control that. The paper mill doesn't pretend to control that, and it's got organics, it's got salts, it's got fibers, it's got slugs and chunks of things as it comes down the pipeline. And we do a couple of things. So the first is that we do put a macro filter, right? So that we can prevent those slugs from hitting the surface of our membrane and damaging them with abrasives. But the majority of the fouling is actually the organics that we're separating out. And so we need those to reach the membrane so that they can kind of be channeled into the concentration stream. We do a couple things. One, we build the system such that at any given time, some of the membranes, some subset of the membranes can be cleaned, and they can be cleaned very aggressively. One of the reasons in specifically the water world why fouling is such a big issue is because if you clean them, the membranes get damaged. They're so fragile. They like water at 20 degrees C at pH 7. And if you clean them with anything outside that, whether it's soap or caustic or acid or enzymes, the membranes start to get damaged. Because we don't have that phenomenon, we've broken that link and we can clean them very aggressively and be able to run, say, pH 14 solution at high temperature to get to dissolve things off the surface of the membrane. And that cleaning cycle allows us to make allows for kind of continuous production through the rest of the system.
Great, thank you very much. So another question is related sort of breadth of the opportunity here. Have you looked at or explored opportunities in metals production?
We have, and both in mining and in metal production, in steel making in particular. What we found with the paper industry is that because of the nature of the industry, the challenges are pretty well understood and pretty public. When we run into manufacturing companies all over the world, every company does it a little differently, and that's the point, right? That's the trade secret around that manufacturing process. And so, sort of to give ourselves a break while we're scaling up the technology and growing as an organization to do commercial deployments and all those sorts of things, we identified a starting off industry that everybody is familiar. It's all very well known that there's a lot of fouling and that there is a high pH stream and things like that. So yes, there is, but of course, with that trade secrets comes all the NDAs that I can't get into any of the details in that separation process.
Okay, good, thank you. So another area that's I think a rich space for reducing energy use and separations is the oil and gas industry. So in refining, in particular. As you know, these industries are very focused on how to reduce Scope 1 and 2 emissions, and in the not too distant future, how to eliminate even emissions from the end use of products. But refining is a big user of energy, a lot of distillation in refining. So what do you see as opportunities there for via separations?
Great question, and it's actually one that I'm personally particularly passionate about. The olefin paraffin separation floats to the top, no pun intended, as a gas separation floats to the top really frequently when we talk about petroleum products. So this is, for example, propane-propylene separation, and it does that because it specifically is so difficult and requires so much energy in the process today. It's not strictly the pasta pot boiling off analogy that in the way it's done today, but it is difficult and it is energy intensive. So we actually have research ongoing in the chemical engineering department at MIT with Professor Zach Smith to identify the use of this material and modify the material specifically for olefin paraffin separations, other gas separations in the petrochemical industry. and see that as a very real future. These membranes have been designed as liquid-liquid separations. They were initially designed for water desalination, and so our bread and butter is liquid separations, but we are venturing into the gas separation space specifically for petroleum.
Yeah. So a question about you cited a number for CO2 released from the boiler application, or maybe that's pulp and paper processing as an industry. Is that true?
So
And what was that number again? And is
Yep.
that just U.S. or is that global?
Great question. So that is global. That's a global number. In the United States specifically, we'd see about a 25 megaton reduction in CO2 if we were in every single mill in the country. And that's about a couple hundred mils. And that is coming from basically the reduced energy per unit paper required, and the number of tons of paper produced. So that's how that number is calculated. Today, I didn't get into the details of it, but when a tree becomes paper, about a third of the biomass becomes the paper, and about 2/3 of the biomass becomes the black liquor, the everything else, the soup of everything that is undesirable in paper, including all the chemicals that are used to do that dissolving process. And the separation itself, the evaporation process as it stands today, is taking that black liquor at about 12% solids and up concentrating, boiling off all the water to get it to about 75% solids before it can then be fired into the recovery boiler, where it is then burned. The steam that comes off of that boiler goes right back into the evaporators to be able to support that system, as opposed to going to other places in the mill, as opposed to generating electricity, which is renewable electricity, and in some scenarios actually qualifies for renewable energy credits as well, or as opposed to being useful in some other capacity. And so that is where that energy offset comes from. And I mentioned it's about 25 megatons for the US. Majority of paper production is not actually in the United States. It's in South America, Europe, and Asia, China in particular, and there's a lot of CO2 offset potential there.
Good. So there's a question about another area, obvious area, was in your chart of different places where membranes are used for separations. Do you see an opportunity for your membranes to compete with RO membranes for desalination?
Excellent question. We're not trying to. RO membranes are actually pretty damn good at their job. They do the separation required, which is pull sodium chloride from water at 20 degrees C at pH 7 in very, very clean environments. In fact, such clean environments that when RO plant is in an RO plant, the water that comes in is chlorinated to kill off all the bacteria and viruses that might be in there. And then it is dechlorinated right before the membrane step, so that it is just water and salt before going through the membrane. On the back end of the membrane, it's rechlorinated so that you don't grow anything else. And then it goes on to municipalities and things like that, whatever the application is. And I think that speaks to the fragility of those RO membranes. So our initial hypothesis when I was in grad school was that a more robust RO membrane would be able to save costs kind of as a whole in the whole plant, as well as improve the efficiency of that reverse osmosis process. And the answer is that it does do that just a little bit. It's incremental. The difference is not enough to really affect the cost of desalinated water, because so much of that cost is in the capital infrastructure, in the permitting, in the distribution, and things like that. And so the challenge with RO is that they're really good at what they do. I do harbor a vision of using this particularly in very challenging to treat waters if they're, for example, very acidic for some reason, or maybe it's like a pharmaceutical, a pretty stubborn pharmaceutical ingredient in the water. The challenge there is the volumes are very high for very small amounts out, and the economics are tough. It's tough to compete with a membrane that has been around for 20 years, as well as has mass production and all the economics of scale, economies of scale that go with that. And so it's not sort of our first focus.
Okay, good. Another question deals in a sort of different aspect of your business is whether you have are there any key policy or business challenges that affect your ability to deploy the technology?
Sorry, could you say that again?
Any policy or business challenges that you're facing that are particularly critical?
Yeah, it's an interesting question because of course, a price on carbon would make everything look more attractive and more economic because that would, the externalities of that carbon emission would be accounted for. But barring that, we work really hard to make our technology and our business model work for the customer. And so the customer is incentivized not because we're greenwashing or because it's good for society to do this, but because it makes sense to their bottom line. When we talk to pulp companies, we're talking to the CFO's office about what this means for their mill level production and what it means for their bottom line. And as a result, it's almost just by accident, or it is by design, but it is sort of it's not the selling point. If you look at a deck that we're talking with customers about, it's a little different because it actually isn't about industrial decarbonization. It's about increasing productivity and reducing energy costs, and process intensification and augmenting their assets that are you may have been built in the 40s, and those are the sorts of things that we're talking about. So I can't think of anything specific that is barring. I will say that we are selling into entrenched industries that have been doing things one way for many years, and the last thing that I want to do is be a kid from MIT telling the paper industry how to do what they've been doing well for 100 years differently. And that's not at all what we're trying to do. We're working alongside and offering a different tool in the toolkit that maybe wasn't available before.
Yeah, no, it's clear that if you can avoid using energy, you're going to de facto save money and reduce CO2 emissions, because a lot of that energy for the boiler there comes from fossil fuels right now, I'm
That's
sure.
exactly.
But even if you switch to hydrogen or some green source as a way to produce the steam or to run the boiler, saving energy will still reduce your bottom line.
Exactly.
So yeah.
Exactly. No matter what you're using, whether
Yeah.
it's a renewable electricity source or a hydrogen source or a fusion source or a fossil fuel,
Yeah.
Using a tenth of the energy is going to cost a tenth of the energy
Yeah.
cost.
Yeah. So one last question has to do with sort of the crisis of the day, which is COVID-19, and whether you see any opportunities for your kind of membranes in addressing that challenge, whether some of the reagents we keep hearing about in short supply, or well, it seems like most everything is in short supply here. So what do you see opportunities there? Have you been approached by people in those businesses, the pharmaceutical business, or is that kind of processing still a little bit too far down the road for them?
It's an excellent question. We have a little bit by necessity been pretty ruthlessly focused on the paper industry. I think the blessing and the curse of a platform technology is the breadth and diversity of different places we
Yeah.
can focus. With that said, we have spent some time thinking about we are experts in porous materials, and that is exactly what a mask is. And so we have talked about what we can do to help with PPE shortages. We have in the past talked with pharma companies about developing new APIs and things like that. We live more in the pharma regime than in the biotech regime, because viruses are actually about 2 orders of magnitude larger than the filtering size that we offer. And so we live a little bit more in kind of the drug development process. And we have, revisited all of the customers, or not all of them, but a good number of the customers that we want to work with in the future, in terms of what does this mean for the paper sector? What does this mean for things like petroleum, with negative oil prices? What does that mean? And so we've kind of been looking at the implications of COVID on our existing industries, and focusing on deploying our pilot. And that's something I hadn't mentioned, which is that we're about 10 months away from deploying a commercial pilot at a facility that is of scale, that all we have to do is make a lot more of them. And so getting to that place while also managing shutdowns in the lab and distancing in physical spaces and things like that has been our focus.
Good. Well, thank you so much, Shreya, for sharing the via separation story with us. Very interesting technology, and looks like it's going to be a big player in helping us reduce energy use and at the same time CO2 emissions. So thank you very much. All the best with the company.
Thank you.